An electron filled with helium is heated at 400 K. A beam of helium atoms emerges out of the enclosure. Calculate the de Broglie wavelength corresponding to the helium atoms given the mass of the helium atom is 6.7 into 10 to the power of minus 27 kg. See here it is kinetic theory of gases is considered, where energy of these helium atoms is given by T by 2 kT. You can note down the energy of the helium atoms in a kinetic theory of gases. Energy of these gas molecules is given by, write down, E, capital E is equal to 3 by 2, 3 divided by 2 K into T. E equal to 3 by 2 K into T, where K is the Boltzmann constant, T is the temperature. That is for lambda equal to H by P, that is equal to H by root of 2 ME, isn't it? So in place of E, you substitute 3 by 2 KT. So here in place of E, you substitute 3 by 2 KT. So 2 in the denominator and the 2 there in the numeric, in the within the root gets cancels. So it is only lambda equal to H by root of 3 MKT. So the formula for de Broglie, that is the wavelength, de Broglie wavelength in this particular case is equal to H by root of 3 MKT. H, Planck's constant as usual, within the roots 3, that is the mass of the helium atom is given to be 6.7 into 10 to the minus 27 kg. K is Boltzmann constant 1.38 into 10 to the power minus 23, and the temperature is 400. You substitute these values and see that it will be around 0.63 angstroms. So now these numericals on Heisenberg uncertainty principle. So the uncertainty in time if an excited atom is 10 to the power minus 8 second. So the delta T, one other expressions for Heisenberg uncertainty principle along with your delta X or delta X into delta P equal to greater than equal to H by 4 pi. So for with respect to energy and time, it is delta E into delta T greater than equal to H by 4 pi. So this is another Heisenberg uncertainty principle. Uncertainty in time if an excited atom is 10 to the power minus 8 second. So it here delta T is 10 to the minus 8 second. What are the uncertainties in energy? It is asked to calculate the uncertainty in energy, that is delta E. Then find the frequency of radiation. So you need to find the frequency of radiation. So use the formula delta E into delta T, that is greater than or equal to H by 4 pi. So what you required, the one of first the one is delta E, the uncertainty in energy, delta E, arrange for delta E. So it is H by 4 pi into delta T. Delta E is equal to H by 4 pi into delta T. So the value of H is 6.626 into 10 to the power minus 34, and here what I have done did is I have taken, since H by 2 pi is equal to H cross, I substituted H cross and divide by 2. I am just doing like that. So H by 4 pi is equal to H by 2 pi into 2, isn't it, in the denominator? H by 2 pi is H cross. The value of H cross is 1.054 in exponent minus 34. It is in joules. Divided by 2, that serves the H by H cross, H by 4 pi. So in the denominator, it is delta T. It is 1 into 10 to minus 8 second. I am converting this energy to electron volts. Therefore, I have divided it by 1.6 into e to the power minus 19. Then it happens to be the answer 3.3 exponent of minus 8 eV. You can check, or you can do is you substitute for this H in the denominator 4 pi, that is multiplied by delta T, that is multiplied by which 1 electron volt, that is 1.6 into 10 to the minus 19. You can try all that way also. The answer will be 3.3 into 10 to the power minus 8 volt. Then using the expression for photon, that is delta E is equal to h nu, E equal to h nu, that is photon E equal to h nu. So delta E is equal to h into delta nu, because h is a constant. The variables are the energy and the frequencies. Therefore, delta E is equal to H times delta frequency nu. Therefore, the requirement is delta nu. Therefore, delta nu is equal to delta E by H. So, we already calculated delta E. Here, what I have done is energy is in joules, isn't it? Energy is in joules. I am not dividing it by this electron volt. So, delta E, I will tell you why I am not dividing it by electron volt, because this Planck's constant is in joule second. Therefore, joule gets cancels. It gives you the unit of frequency, it is only per second. So, that is hertz. Therefore, I have expressed this energy joules above, that is H into nu. That is photon. We already calculated about delta E. If you, that is again, if you multiplied by this electron volt 1.6 into 10 to the power of minus 19, you will get this value. So use that and you will find it is 15.9 hertz. Then we'll move on to the next numerical. An electron is confined to a potential well of width 10 nanometer. Imagine the electron is confined within the delta x is equal to 10 to the power minus 9 meter. So, electron is confined within 10 to the power minus 9, it is nanometer. Calculate the minimum uncertainty in its position. Therefore, delta x here delta x is 10 to the power minus 9. Then calculate the uncertainty in velocity. So, formula is delta x into delta p greater than or equal to h by 4 pi, where p is the momentum. We can split the momentum to mass into velocity. Therefore, delta x into m delta v, we can rewrite that delta x m delta x into m delta v. M delta v is nothing but the delta p. Therefore, you get the delta v from there. Delta v is equal to h by 4 pi times m into delta x. Okay, if you rearrange, you will get the delta v. That delta v is the uncertainty in its velocity. So, that is equal to h by 4 pi m into delta x. H is Planck's constant as usual, divided by 4 times pi into mass of the electron 9.1 into 10 to the power minus 31, and delta x, it is 10 nanometer. So, 10 into 10 to the minus 9. If you do this, you will get around 5.8 kilometer per second. This is the uncertainty in velocity. Then we'll move on to the next numerical. If the kinetic energy of an electron known to be 1 electron volts. So, here the kinetic energy is equal to 1 electron volt, must be measured within point 0.001 eV, that is delta E. So, delta E is around 0.001 eV. What accuracy can its position to be measured simultaneously? So, you need to calculate the delta x. So, as usual, formula delta x delta p greater than equal to h by 4 pi. So, you need to calculate for delta x. So, delta x is equal to h by 4 pi into delta p. So, what are the things, the data, according to the data available here is kinetic energy, that is E equal to p square by 2m. So, now you know that, so if you change E to delta E, look at there, I would differentiate it with respect to P, dE is equal to 2p into dP divided by 2m. So, left hand side, that is E equal to p square by 2m. So, 2m is 1 by 2m is constant, common constant, you keep as it is. So, dE is equal to 2p into dP. That is why you do the differentiation, isn't it? dE is equal to 2p into dP by 2m. So, that is delta E. From this expression, you will get delta P. So, 2 gets cancels in the second equation. So, you got one delta P is equal to m by P into delta E. So, the momentum P delta P is equal to the change in momentum is equal to m by P into delta E. You substitute this into formula in the formula of delta x. Delta is equal to h by 4 pi. In place of delta P, you substitute this m by P into delta E. So, if you rearrange, you will get the expression is equal, that is equal to h by pi into delta E within the root E by 4m, you will get it. You try. So it can be simplified, delta x can be simplified to h by pi into delta E, and within the roots E by 4m. And now you have the values now. H is Planck's constant, pi the value now. Delta E is given to be 0.0001 eV, that is the probable accuracy in the energy, that is delta E. 0.0001 EV. So you substitute for EV also. So 0.001 into 1.6 into 10 to the power minus 19 should be considered here. In place of delta E, use substitute 0.00, I mean that is 3 zeros 1, 0.0001 into 1.6 into 10 to the power minus 19 should be considered. And within the brackets above, within the square, I mean so root, within the root, E is equal to 1 EV. So it is 1 into 10 to the power 1 into 1.6 into 10 to the power minus 19. So in place of E, it is 1.602 into 10 to the power minus 19 joules. 4 times the mass of the electron. 4 into 9.1 into 10 to the power minus 31 kg. If you do that, you will get around 1 micron. Value of E is 1 EV. Kinetic energy, that is kinetic energy, is equal to 1 electron volt, that is equal to 1.602 into 10 to the power minus 19. You take E is equal to 1.602 into 10 to the power minus 19. An electron and a 150-gram baseball. We got two objects here. One is electron and other one is baseball, of whose weight is 150 gram, are traveling at a speed at a velocity of 220 meter per second. So both electron and this baseball are moving at a speed of 220 meter per second, measured to an accuracy of 0.065%. So the accuracy in the measurement is 0.065%. Calculate and compare the uncertainties in position of each of them. So you need to calculate the that is uncertainty in its position delta x for electron as well as baseball, with an accuracy of 0.065, and assumed to be they are moving with the same speed velocity 220 meter per second. Only thing that is changed is the mass of an electron, and this mass is equal to 150 gram. So what we are doing in this numerical is that again we are testing the validity of the this Heisenberg uncertainty principle with respect to an electron and the baseball, and we will come to some conclusion at the end. So now the formula as usual, delta x into delta p, that is equal to greater than or equal to h by 4 pi, that is the basic equation of uncertainty of momentum under this position. So here as given, we don't have straight away the momentum. So momentum is equal to mass into velocity. So we split delta p is equal to m times delta v. Since he already given the velocity 220, so we'll calculate the uncertainty in its velocity, that is delta v, that is equal to velocity, given velocity is 220 meter per second, with an accuracy of 0.065%. You know how to calculate this. So velocity is equal to 220 multiplied by 0.065 divided by 100, that gives a percentage. Okay, so delta v in percentage, so with accuracy of 0.065. So delta v happens to be, if you do this calculation, it is 0.0143 meter per second. Delta v you will get is equal to 0.143 meter per second. Use this into the expression for the uncertainty principle. Therefore delta x E, that refers to electron, that is equal to h by 4 pi times m into delta v. So h is 6.626 exponent of minus 34, 4 pi in the denominator 4 pi, and mass of the electron 9.1 into 10 to the power minus 31 it is, okay, you make it 31, it is not 34, it is minus 31 into 0.143. If you do this calculation, you will get around 0.2 mm. And if you similarly continue with the baseball, only thing you change in the next one is the mass of the base ball, it is 150 gram. In place of mass of the electron, you substitute 150 gram, that is 0.15. And if you do the calculations, you will get delta x uncertain position, delta x with of the base ball in uncertain its position is equal to 1.2 into 10 to the power minus 33 meter. See, the change of the position is only 1.2 into 10 to the power minus 33. Remember, it is minus 33. So it is very, 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 very small. You cannot observe it at all. This millimeter, nanometer, angstroms can be easily observable quantities. With respect to an electron, delta x is happens to be 0.2 mm, the millimeters. It's quite easily an observable, physical and measurable value and an observable quantity. With respect to the base ball, the change in the position, uncertainty in its position, is of the order of 10 to the power minus 33. That is 1 divided by 1 followed by 33 zeros. So such a small quantity can never be observable, the physical world. So if you apply the Eisenhower principle to at the macroscopic scale, macroscopic particles, the observation leads to be very minimal, never be a physically an observable quantity. So it upholds the microscopic particles, and it will not able to, and we will not be able to understand or the feel the measured quantities. An electron is confined to a box of length 10 to the power minus 9 meter. So it is nanometer. Calculate the minimum uncertainty in its velocity. An electron is confined to a box of length, that is delta x. Delta x is equal to 10 to the power minus 9 meter. Calculate the minimum uncertainty in its velocity. It is not said they calculate the uncertainty in velocity. They have put a condition minimum uncertainty. It is not the uncertainty in its velocity, it is a minimum uncertainty. You know that in the last previous class, you have seen that delta x and delta p, they are inversely proportional. They are inversely proportional. If delta x is maximum, then delta p happens to be the minimum. Okay, since they are inversely in nature, delta x is maximum, then delta p is minimum. If delta x is minimum, delta p happens to be maximum, like that way. So use the Eisenhower principle. If you write delta x maximum quantity, if it is maximum quantity, multiplied by delta p minimum quantity. Now I did not take it is greater than or equal to h by 4 pi. To make the overall calculation simpler, I just taken the Planck's constant. Okay. You can also try with h by 4 pi also. To make the calculation simpler, this is the simplest, so I just take only h. You can calculate and check with a h by 4 pi. Okay, no problem here. So now, uh, according to the data available, delta x maximum, that is the length of the box where within the electron can remain. The maximum value it is allowed for displacement is a nanometer, so 10 to the minus 9. So delta x maximum 10 to the minus 9. Then what is delta p minimum? If see, I told you momentum p is equal to mass into velocity. Delta p is equal to m into delta v. In the numerical is asked minimum velocity, minimum uncertainty in velocity. So you calculate first delta p, then split into m into delta v. So delta p minimum is equal to h by delta x maximum. You know, h is Planck's constant. Delta x is 10 to minus 9 meter here. So you will get around 6.62 exponent of minus 25 kg per meter. Okay, that is delta p. Now we require here it is delta v. Therefore, delta p minimum is equal to m into delta v minimum. Therefore, delta v minimum is equal to delta p minimum by m. You divide by mass of the electron. That is momentum delta p divided by mass. So 6.6 you already calculated above there. It is into 10 minus 25 divided by mass of the electron 9 into 10 to the minus 9, 9.1 into 10 to the minus 31. If you do this, you will get delta V minimum is equal to 7.3 exponent of 5. Okay, that is a meter per second. You will get this value ultimately.